Welcome back. Today we're going to cover two topics that are related, covariance and correlation. Correlation can be quite useful. You've already encountered it as a kind of standardized effect size measure. Covariance, by contrast, is something of a behind-the-scenes number. It plays a role in many statistical procedures, but rarely does it appear in a results table. The concept of covariance should be fairly straightforward, though, if you understand variance well. Variance, as you may recall, is the sum of squared case-wise errors, that is, each case's deviation from the mean or from another model prediction is squared, and add it together, then divide that by the degrees of freedom, the number of cases minus 1. So put differently, the sum of squares in the numerator is error for case I times error for case I, the same case. But what if instead of error on a single variable times itself, we multiplied error for one variable, say x1, times the error for another variable, x2 or y? This is called a cross product. If either error is low, that is, either value is near the variable mean, the cross product will tend to be low too. Now, if we replace the sum of squares in the variance equation with this cross product, we get covariance. That is, if the numerator now is the sum of xi minus the mean of x times yi minus the mean of y, or the estimates of x and y, this represents some portion of the variance or spread of one variable that can be explained by the other. If covariance is negative, then as one variable increases, the other tends to decrease. If it's near zero, there's no consistent association, and if positive, they tend to move in the same direction. Now, unfortunately, raw covariance is not a standardized measure. Neither is variance, of course, but at least it's simpler to convert it back to the units of a single variable, a standard deviation, because it's one quantity squared, or based on one quantity squared. So, if values on one variable are multiplied by 100, for example, covariance will be multiplied by 100. This also means that variables with very different scales may not produce reliable estimates of the covariance, because one will tend to dominate the other. Fortunately, we already have most of the tools we need to solve this in standardization, but with one difference. Our goal now is not to have each variable standardized, but a covariance with a standard interpretation itself. So to do that, we multiply the denominator, that is n minus 1, times the product of the standard deviations. So instead of just n minus 1 on the bottom, we have n minus 1 times standard deviation of x1 times the standard deviation of x2. We leave the top as that sum of cross products. This results in a covariance that ranges from -1 to 1. Just like raw covariance, 0 means no association, but now because we've converted the units, +1 means a perfect parallel association, -1 means a perfect reverse association. If that sounds vaguely familiar to you, though with weird words, it's because what we just calculated is Pearson's product moment correlation coefficient, usually just called correlation, or R. An R of -1 is a perfect negative correlation. Each increase in one variable always means the other decreases a given amount. They don't have to be the same number. You could have an R of 1 where the slope is 10. So for each 1 unit increase in the one, it's 10 in the other, but every point would lie exactly on that line. If it's +1, it goes up. If it's -1, it goes down. Now, be careful. Correlation can seem very straightforward to interpret. But what is a large correlation is not always clear. First of all, to understand this, we need to try squaring the correlations of the two variables. You do that, you get, unsurprisingly, r squared. But r squared has an interpretation that's sometimes helpful, because we've now put it back on the same scale, that is a squared scale, as variance, with a range that goes from 0 to 1 now, because the negative numbers aren't negative anymore. R squared is equivalent to the proportion of the variance in one variable that's explained by or associated with variance in the other. Now remember, that doesn't mean we can state causality. We can't tell which causes which if either causes the other, but we can interpret. An R of 0.2 has an R squared of 0.04, or 1/25th of the variance in one variable is explained by the other. 0.8 would mean an r squared of 0.64, meaning that by controlling for that one variable, you could decrease the error variance by almost 2/3. R squared can be calculated for more complicated linear models too, and because of that, it allows us to compare the explained variance as a measure of relative fit, i.e. just adding variables explain more of the variance in our dependent variable or variable of interest. Not only that, you can also calculate significance or p-values for R using a t or z distribution, like normal, and some fancy math. Like other statistics, you can compute a confidence interval and use bootstrapping or Bayesian approaches to produce robust estimates of both the coefficient and the standard error. Usually, it's better to just let the computer do that for you, which is why we're not going to talk about what it actually takes to do that. But you do need to know which to look for. How do you do that? Well, correlation is a type of linear model. If you don't believe me, go to a computer and estimate the significance of a bivariate relationship using correlation and OLS regression. They'll be exactly the same. The numbers won't be the same, but the significance will. Thus, standard correlation estimates are subject to the same limits we talked about. If the effect is nonlinear, variables are not of the correct types, for example, our estimates may be off. If the errors are non-independent, that is, if error in one variable is related to error in the other, or if the errors are heteroscedastic, that is, error in one depends on the value of the other variable, then standard errors and significance tests will be biased. Shouldn't be a great problem since software packages give you the tools to easily adjust, but it's up to you to notice and decide when you need to use those robust estimates. At any rate, the main point here is that correlation is a standardized measure of covariance, and covariance is just like variance, but for two variables instead of one. So although it looks different, correlation is closely related to the rest of the statistics you've seen. If you can remember how it's calculated, it'll help you understand what's going on. If you remember its interpretation and the interpretation of R squared, that'll help you explain it, think about its meaning. And if you remember the assumptions and limits, you can keep from ending up looking really silly by describing a correlation that isn't really there, or saying something isn't there when it actually is or would be significant if you used the correct methods. So, covariance, correlation. Correlation is also called Pearson's correlation. Our covariance we don't see a lot, but it's underneath things. And it's helpful to understand, particularly when you're trying to think about what does correlation mean, which then is closely related, as I said, to some of the coefficient estimates and things that we're going to start getting in our linear models. So thanks for watching, thanks for holding on, have a great day. We'll see you soon.